So this is my Python code and screencast for data analytics CA2. So in this we were asked to implement gradient descent for batch and the stochastic gradient descent. So this is the code for my stochastic, and it's another way of getting the gradient descent. However, this is seen as the most efficient way. Unlike the batch has a list of different step sizes to take, whereas this one, the stochastic, focuses more so on reducing the gradient by taking one point at a time throughout our set. So, like the others, it's the same steps. So we have our initial guess at v, which is here. We're just generating a random point. We set our step size, which is 0.001, and then we need to calculate our gradient first. So we calculate our gradient here, and instead of using the sum of squared error functions, we just use our squared error because we're not summing up all of the points, we're just taking each point at a time, so it's just a squared error. Then the next step is to take a step in that direction minus gradient. So you can see in our function here, we're taking a step in the direction minus the gradient, and we're zipping our points together so the data sets correspond to each other. And so basically, this here, because we're looking at each point, we're using indexes. So after we generate our point, we set our step size, we set our iterations with no improvements to 0, our min v is none, and our min value is float infinity. So in our while loop, we set our value to the sum of the squared error for index I, whichever in x, and index I, which is the point in y that it's iterating through, and we're zipping them together so they correspond. So if our value is less than our minimum value, min v and min value will be set to v and value. Our iterations with no improvements will stay as 0, and our step size is still 0.001. And if we have an iteration with no improvements, we plus 1. And we also multiply our step size by 0.9. So then next, our indexes here. We're setting our indexes for I in indexes, so we're getting again the index, whichever position I in x is set to xi, or xi is set to position I in x, and then same again for y. So then our gradient I, which is the gradient at that point, is equal to, we call our estimate gradient s function. It's just the squared error, it's not sum of squared errors. And we're passing in our value, the index in x that corresponds to the index in y, and then we're setting our v, or we're telling our v, to take a step then in that direction of our value, or we're passing in our value, our gradient, and our step size. And this is our result. So you can see that this is the point throughout our two data sets. This is our x and this is our y. That the squared errors is at its minimum from our initial guess v.